Okay, so we're going to run through this International Mathematics Olympiad problem from 2015, and essentially we've got these terms in a sequence A1, A2, so on. They're all positive terms. The terms satisfy this inequality here, so the term ak plus 1 is greater than or equal to k multiplied by the previous term ak over ak squared plus k minus 1. Okay, so, and the objective here is to prove that the sum of the first n terms is always greater than n for n greater than or equal to 2. So the first thing we notice here, this proof for n greater than or equal to 2. Obviously, when we're dealing with terms in a sequence, we're looking at n in the natural numbers. So this suggests induction. Okay, but first we have to look at find out some more information so that we can make some sort of induction argument, because right now we don't have everything we need to solve this question. So the first thing we do is we rearrange this inequality to look for some formula in terms of AK. So bear in mind the terms here are positive, so this k is positive, ak plus 1 is positive, k squared is positive, k minus 1 is positive, this ak squared plus k minus 1 is all positive, because k minus 1 is greater than or equal to 0. So we can flip these things round. Okay, so we're first going to divide by k, and then we are going to flip the inequality over. So we're going to get k over ak plus 1 is less than or equal to ak squared plus k minus 1 all over ak, and that is equal to ak plus k minus 1 over ak, and that implies that ak is greater than or equal to k over ak plus 1 minus k minus 1 over ak. Okay, so that's just subtracting this term from the inequality. So why is that useful? Well, now we've got some sort of bound on ak, and although it involves ak here, this minus sign and the fact that we've got an involvement of ak plus 1 here and ak, with the sort of symmetry of the problem, we'll see when we sum up the terms we get a lot of cancellations, and we'll run through that now. So now we look to sum up the first m terms, so we get a1 all the way up to am, and now we know a1 is greater than a certain inequality using this, plugging in k equals 1 all the way up to am. So using that we can see that this whole sum is greater than or equal to, okay, so plugging in k equals 1, we get 1 over a2 minus 0 over a1, and then I'm not going to run through all this, but if we keep adding these up, we get finally m over am plus 1 minus m minus 1 over am, and obviously this term is 0, so this goes, and it turns out, and if you think about it, you can reason that this term cancels out with what's in the next bracket. Okay, all these terms cancel out, that this one cancels out here, and the only term we're left with is this one. Okay, so now we see the benefit of this. Now we've got some sort of bound for the sum. Okay, so now we know that the sum of the first m terms is greater than or equal to m over am plus 1. Okay, so that's some useful information that we can. Before we move on, I forgot to mention that this initial result we're given is labelled 1, and in the solution, or you can call this whatever, but this is labelled as result 2. Okay, so we can reference these later on without writing them in full. Proof by induction, we start with the case n is equal to 2. and then we consider the sum we're after, so a1 plus a2, and for this particular case we want to show this is greater than or equal to 2. By result 1 we know this is greater than a1 plus 1 over a1. This is by using the result to show that a2, this term here, is greater than 1 over a1, and this is greater than or equal to 2. So we're done for case 1. And now for our induction step, so we assume the result's true for some n greater than or equal to 2, and then we're going to consider can't even spell, consider case n plus 1. Now our assumption that this is true for some n greater than 2 means that we have a1 all the way up to an greater than or equal to n. So when we want to consider the case n plus 1, we're considering the sum a1 plus an plus n plus 1, and we want that to be greater than or equal to n plus 1. And this result here is obviously true if an plus 1 is greater than 1, so we're going to consider that as case 1, and that should be an plus 1 greater than or equal to 1. And now all that's left to do is consider case 2, so that's to show that this is true even when an plus 1 is less than 1. This is slightly more complicated but not too bad. So we're going to use result 2 now. So again, we're considering the sum of this added to n plus 1, and using result 2, this first part of this sum, we know that that's greater than or equal to n over an plus 1. Okay, that's the result we found earlier. Then we're going to add on our terms still in the end, and then this part here on the right hand side is equal to, and this is a little trick we use sometimes, where we add on a term and then subtract it. So we've added on another 1 over an plus 1, that means we get an n minus 1 here, plus n plus 1. Okay, but because an plus 1 is less than 1, this section here is greater than n minus 1, and this is greater than, don't need an equals here really, is greater than 2. Okay, and of course n minus 1 plus 2 is equal to n plus 1. So again, we've shown it's true in this case, and that's the end of our proof. So now just some final comments on the method. I'm sure most of you, as we've gone through this question, will follow because you're familiar with induction, and by reducing sums in the way we did, where we get those cancellations, that's all been seen at A level. By looking at case-by-case analysis, and by using inequalities, we've all worked with those things before. The question becomes, how do you manage to bring all that together in a way that solves the problem, when the pressure's on? And that's the tough part. That's the challenge of these Olympiad style questions, and that just takes a hell of a lot of practice and lateral thinking. The signs were there, like we pointed out. It seemed obvious to begin with that proof by induction would be needed, and then you just have to sort of trial things, see where they're going. If it's not working, start a new method. Like I say, that's definitely the tough part, is figuring out how to get into these questions in the first place. But yeah, I hope you enjoyed this video. We will look at some more Olympiad questions if you like, because I think they're good, interesting questions we can get into. But anyway, thank you for watching this video, and I hope to see you in the next one.